Okay, just a short talk about the oxygen cascade. So what does that relate to? Well, the oxygen cascade relates to the drop of the oxygen pressure as we go from room air step by step eventually to the mitochondria inside our cells. And mitochondria, if you remember, is a organelle. It's a little internal organ inside the cell, and its main function is to produce energy, and it does that hopefully aerobically, and it burns then glucose with oxygen. And therefore we're now going to have a look at how oxygen gets from room air into the mitochondria. So there's one really interesting aspect, at least for me it's interesting, and when I first encountered it, and that is that a gas can remain a gas but at the same time be dissolved in a fluid. So for example, we have a fizzy drink, a Coca-Cola, or if you're a bit more fancy, like I like to do on the weekend, open a bottle of champagne. As soon as you take the cork or the lid of the bottle, you see air bubbles come out of the liquid and they reach for the surface. So that idea is that the pressure above the liquid is reduced by opening the bottle, and hence the solubility of the gas in the liquid has changed. So a good example of that is the bends, where people go deep sea diving. When you're very, very deeply in the ocean, the pressure of the water is enormous, and your body can dissolve way more oxygen than at ground level. And if you would go back to ground level out of the ocean, above water, too quickly, then the solubility of oxygen decreases too quickly, and you get air bubbles in your blood, and that causes an embolism, and it's called the bends. Alright, so now we've just looked at that practical example. Let's see how this works. So in room air, we have a pressure of about 1 atmosphere, which translates in 760 millimeters of mercury. Now room air for 21% is oxygen. That means that the partial pressure of oxygen in the air is 0.21 times 760, which is 159.6. And that is approximately 160 millimeters of mercury. So now we start inhaling that air, go through the nose and mouth, our throat, which is called the larynx, then through the voice box, which is called the larynx, and goes into the windpipe. And once air has reached the windpipe, air with oxygen, then we find there's humidification happening of that air, and oxygen is no longer 21%, meaning that it has dropped to 150. Then if we further go down to the alveoli via the main bronchus and the bronchioles, we end up in alveoli, alveolar sacs, and the pressure now has dropped to 105 because of the admixture of other gases. And so that 105 is the driving gradient pressure to press air from a higher pressure to a lower pressure. Your venous blood is low in oxygen, and therefore your blood starts oxygenizing. And we call that gas pressure in your arterial blood PaO2. Now, a lot of you are familiar with the pulse oximetry. And with pulse oximetry, you measure the oxygen saturation of hemoglobin. So your body wants more oxygen than it can dissolve in blood, so therefore it has a carrier protein with an iron atom inside of it, and that's called hemoglobin. It's found in red blood cells. So we're going to later look at the relationship between the arterial oxygen pressure and the saturation of hemoglobin, but it's not the same, and you must remember that it is the arterial oxygen pressure that gets oxygen to the cells, and the only way to find out what that is through taking a blood sample and analyzing it in the blood gas machine. Alright, so we go to 105, and then the arterial oxygen levels will be about 80 to 97. So it tends to drop as we get older. There's a little formula, I think it's 109 minus 0.43. times your age, and then you get a number. I don't know how well that formula works. You can usually take a blood gas and see what it really is. And see at the mitochondria, we can come, and if you read the textbooks, to an oxygen pressure anywhere between 1 and 10. So an average of about 5. So we started with 160 and then we end up with 5, and that's called the oxygen cascade. So let me go back. Yeah, we start 160-ish, in the windpipe 150, then the alveoli 105, up blood 80 to 97, and eventually that oxygen is pressed through the interstitial fluids, intracellularly, and then from the intracellular plasma into the mitochondria. Now imagine that we're giving supplementary oxygen, yeah, and then suddenly we're seeing that the fraction of oxygen is no longer 21%, but maybe it can go up to, say, 40. If we have 40, then we need to change this formula to 0.4 times 76, and we see we get an oxygen pressure, which sits around 310. And then we're cascading down to here. We then suddenly see that the arterial oxygen pressure goes up to 180s, and I've seen fraction of inspired as high as 70% run intraoperatively, which meaning if you take your blood gas intraoperatively, you can end up anywhere between 180 or 240 or even higher. All right, so that's the first step. So step 2 is to look at this diagram, graph, whatever you want to call it, and it's called the hemoglobin oxygen dissociation curve. Long word. But what we're really doing is we're looking at the relationship of the arterial blood gas pressure of oxygen. So 0 pressure here, here 80 and 97. And at this other one here, I've looked at the oxygen saturation of hemoglobin. So usually we call that saturation or SATs. Without the sets of a patient, you will hit that set. Yeah, we mean that one. And here I've marked 94 and 100%. So normally people are between 94 to 98% saturated, meaning that a fair amount of the hemoglobin has oxygen on it. And remember, that oxygen is sort of like stored in a backup tank, if I may call it a tank. But purely that's a backup. It is the blood gas pressure that works through a gradient as the driving force to get oxygen eventually into the cells, into the mitochondria. So normally are 94 to 98. Often we give patients supplementary oxygen. That means that they don't start off with 21% fraction of oxygen, but maybe 30 or even 40 or higher. I've seen even 100% sometimes when we induce patients, particularly on the high flow humidified oxygen machine called OptiFlow. So anyway, what's important to see is this relationship and the curve. So this dotted line is 80 and this dotted line is 97, meaning that's what the normal range of the blood pressure is in your arteries. And if you look 97, we usually should have saturations close to 100%, right? Yep. So if we go to 94%, then see the dotted line corresponds to 80. So this zone is normal, and therefore 94 or higher, usually up to 98, is normal and everything's fine. But as soon as we go underneath 94%, see this huge and fast steep curve coming down. We quickly start to lose our backup tank of oxygen, meaning that our blood actually gets low in oxygen, and that's called hypoxemia, and eventually the tissues and the cells get low in oxygen. That's called hypoxia. So this is one of the standard things we do with patients. We look at the oxygen sats. The other thing, of course, is the blood pressure, which we talk about in another little video. So keep in mind the oxygen cascade, that's the driving force to get oxygen in. Then we have a backup tank with hemoglobin, and the association is such that the normal PaO2 is between 80 and 97, and it corresponds with saturations that are between 94 to 97.